I was asked to clarify the issue with an issue with the HLV inclusion problem, which HLV really didn't deal with that in his solution. The solution was simpler, but eventually people made it more and more complex. And I mentioned the work of Mura. There is a very nice book by Toshio Mura, uh, which is called Micromechanics of Solids. The title is a bit misleading because it's mostly all about treating problems with inclusion formulation. But this is a very nice book, really. I mean, if you are into the field, just try to get hold of it. And so the thing is that when you have the stress in the grain and you write it as the elastic this is elastic problem. The sigma in the grain is the epsilon in the grain total minus the epsilon g of transformation. So this is a plastic transformation. So the total minus the transformation give you the elastic strain. Now you can one trick consists in adding and subtracting Cg times Eg. So you write this as the C in the medium times Eg total minus Cg minus C average Eg total plus Cg Eg minus C transformation. And then you say, okay, I'm going to write this as C times Eg total minus ta, 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 C minus Cg. I'm not sure I'm getting all the signs right, but C minus Cg, Cg. Anyway, what I'm coming to here is if you add and subtract the right terms, you end up with in this case is Eg. So Ceg, this minus is coming here. This Eg is here minus Cg E transformation. So you can say that this term is a fictitious transformation, E transformation, and so this problem will look like you have a medium with an inclusion with the same constants as the matrix. This is the strain in the inclusion minus a certain fictitious transformation. So you homogenize your problem by defining a transformation strain that takes into account the difference in elastic constants. So that's it. I mean, I don't need to erase it. Okay, let's get started with the with the lecture. Today we are going to look into a couple of problems that make use of the fact that we mix sometimes the strain rate and the stress components that are applied, but it also has to do with yes, how we deal with boundary conditions depending on the type of test that we are doing. So this is in principle an illustration of the channel die test. You are probably familiar with it. The channel die test is this is your channel. So you put your sample, you put your parallelepipedic sample inside this channel, and then you compress it with a tool that is like that. You compress it. So what happens is you are preventing this sample. This sample is going to be compressed in this direction and to be stretched in these other two directions. Now, it is prevented from shearing in many directions, and that is what this example means to illustrate. So you see how the velocity gradient is used in the code. So here you see that this component L21, which is delta U2 with respect to x1. So this is how much the displacement changes in the direction 2, how much the displacement changes in the direction 2 when you move along the direction 1. So it will correspond to this type of shear, but this type of shear cannot take place in the channel. This type of shear delta will correspond to this one. Let's take L12. This corresponds to the change in the displacement in the direction 1, U1, as you move along x2. This one can take place. There can be a delta difference in displacement as you move along the direction x1. So this one can take place. This one, L13, for the same reasons, this one can take place, but this one cannot take place because it would be shear against the walls of the die. So these four shears cannot take place. So the components 21, 31, 32, and 3 have to be imposed equal to 0. Have to be imposed equal to 0. The component L33 is the compression, and L22 is the strain in the horizontal direction, which again the channel prevents it. It's 0, is imposed, and L11 is equal to minus L33 just because the problem is incompressible. So the diagonal, the trace of this tensor has to be 0. And then L12 and L13 are not known. You can have, if your texture is not orthotropic, you can develop shears as you compress your material. And so the condition is sigma 12 equals sigma 13 equal to 0. Then now, of course, this assumes that you have no friction at all, and that the material, when you compress it, is able to shear. Now, if you have friction, the code VPSC allows you to put a value there. You can put 100 MPa, but I mean it's a value that you can set. But to do it right, one should link that value to some friction model. To set that component, but in principle it doesn't have to be 0. It can be a given value which would be the value of the friction, but you have to put something in the process file. So I had prepared an example, but I'm going to skip it. But to do the example, and if you want, you can do it by yourself. I'm going to explain the problem though, how you deal with it, and then if you are welcome to do that as an exercise. The example 6 in the distribution that you got is torsion. And torsion really, in this case, is torsion of a thin wall tube. So when you have a thin wall tube, and thin wall typically is that the thickness of the tube, the thickness T, is about the radius divided by 10, something like that, in that order. So if you do shear here in this tube, this element, the solid part of the tube, is deforming by shear. So you can think that that problem is a problem where you have an element here like that, and you are shearing it. You are shearing it in this direction. So this is really the condition that we are going to be imposing. So if the tube is thin, it is okay. If not, you really have to solve layer by layer and couple the layers because they cannot shear independently of the next two neighboring layers. So you have to solve the problem as a coupled problem, and it is possible to do it, and we have done it in the past with a collaborator, but I'm not going to be talking about that. What I want to mention here is that when you shear a tube, you can do it in two ways. One is you keep the tube constrained so the length cannot change. So you grip it in such a way that you're shearing, but the length cannot change. Or you can leave one end free, and that is a free end tube, and then when you shear the tube, this end can slide in or out, and the length can change. Now, that gives different results, and this is a problem that was studied by a guy called Swift in the 1930s, I think. But he did it with wires, not with tubes. He did it with wires. He figured out that if you torsion a wire, it changes the length. And he couldn't really explain why, because the concept of texture was not present. The reason why the wire of Swift, that is called Swift effect, the wire of Swift was changing length is because as it developed texture, the material tends to activate systems in such a way that in addition to accommodating the torsion, it is also giving you a component of changing length. This is what this problem will lead to. So here the two problems that you are going to find in the examples are when you say, okay, in the direction 2, I say that there is no displacement. L is 0, that is a fixed end, but I don't know what is going to happen in the direction 1, in the direction 3. So the tube can become thinner or thicker, and if it does, it will also expand in the tangent direction in order to preserve the volume. So those two things can happen, and they do happen. And then you impose the shear 1, 2, you put force on this plane that is pointing in the force in the direction 1, that in this plane that is pointing in the direction 2, L1, 2. And then the other two shears have to be 0 because it can be demonstrated that the plane of the formation has to remain planar, that it cannot start moving around, because if not, well, that it can be demonstrated that that's the case. So the other problem is the problem of free end. You don't know any of the diagonal components of the velocity. You don't know if it is going to change length or not. You don't know if it is going to increase the diameter and reduce the thickness. So these are not known. The complementary stresses are set to 0 then. The complementary stresses are set to 0. And the other components, the same story as before. In this problem, the hardening that was assumed to do the problem is that there is linear hardening. From tau 0, it grows linearly, the critical stress in the system. So you will have a control file like this, where in this case we do 40 steps, 100%, and then we calculate the yield surface, and then we do another 40 steps of 2.5%, that is another 100%, and we calculate again the yield surface, and we plot the components of the 1 and 5 of the yield surface, which is the stress sigma 1, 2, which is the stress that you are applying to your tube, and sigma 1, 1, that because sigma 1, because sigma 1 is 0, that's the boundary condition. This is the sigma 2. So that is the compression stress that the tube is going to experience because you are holding the end. So you hold the ends, it tends to expand, but if you don't let it expand, it will develop a stress. So the textures are very similar, but they are not quite the same. They are slightly rotated. This is the after 100%, after 200%. This texture is slightly rotated with respect to that texture, but that is enough to give you some effects that we will see. So this is the kind of texture that you should get if you run the example. No? Now the interesting thing is how do you analyze this problem from the point of view of the polycrystal yield surface? So here we are plotting sigma 1, which we said is proportional to sigma 2, that is the compressive force, axial force, and sigma 5, which is the shear component. So if there is a compressive force, you are at this point in the yield surface. So this point is such that the strain rate is perpendicular here, because this vector that is perpendicular has an epsilon dot 22, which is this component, equal to 0. You are forcing epsilon dot 22 to be equal to 0, so it has to be perpendicular. So if you have the yield surface, you look where the strain rate is perpendicular to it. That is the point where you are going to be activating the stress state, sigma here. Now, this is for 100% deformation. As you continue the deformation, as you can see, the yield surface tends to rotate, and now the normal force there. So the forces go from compressive to tensile. If you hold the ends, it starts going from compressive to tensile, and then you can see here, if you plot sigma 2, sigma 2 starts at 0, goes through a minimum, and then keeps climbing and becomes positive. Sigma 1, 2 goes practically linear all the way. Now, the problem of the free end, you want now to be in a state where the sigma 2 is 0, so sigma 2 equals sigma 2 is 0. So you need to be along, the stress has to be vertical here, because that is a component that doesn't have a sigma 2 axial stress. But then you get, at this point, you get a normal to the yield surface that gives you a positive strain rate, which means that a positive strain rate in the axial direction means that the length is going to increase. And that is what happens. Sigma 1, 2 here is similar to the one that we had before, but if you look at the epsilon 2, which is the axial, the epsilon 2 just keeps increasing. Now, the hoop strain becomes negative. It means that in the radial is practically 0. That means that the tube is expanding and it is shrinking, but the thickness is not changing. Okay, so that is how you analyze this result. It's a relatively simple system, but it really allows for a lot of insight into this problem of how releasing some of the boundary conditions or imposing boundary conditions changes the way in which your material behaves and responds, and also is very interesting for doing this type of analysis, because it gives you insight of how these things interplay and are connected. Okay. So, the problem that we are going to be discussing next is the equal channel angular extrusion. I don't know, I guess that you are familiar with this problem. Are you, who hasn't heard about the equal channel angular extrusion? I can explain what it is. Okay. So, the equal channel angular extrusion is a technique that 20-some years ago was touted as being the new way of processing material. You can deform your material a lot without reducing the dimensions, and in the process you reduce the grain size. So you have a material that has small grain size, high strength, but when you process it, it's not like rolling, that every time that you roll, your material becomes thinner and thinner, and finally you cannot use that for many uses. So in this case, the material was supposed to retain the same dimension. So it consists, you introduce your sample in a channel die that has an angle here, and so when it goes through the corner of your channel die, the sample shears. Actually, I drew it parallelepipedic here, but it will be sheared. The grain shape will become elongated. The grains become elongated because you are enforcing a lot of shear going through this angle, through this position. And then what you can do is you can turn your sample, put it back there, and push it again. And then again and again. I mean, it's easy to say, but there are a lot of issues with this test. And sometimes the sample fractures, so they have to put a back stress. They also put a plunger on this side to create more pressure in the sample. I mean, there are a lot of practical issues, but eventually people have managed to do magnesium and aluminum components, some titanium, aluminum, titanium components that they have used for building small pieces like prostheses, like the screws that they use bone fractures to hold bone fractures, things like that. But very small, in general, small pieces. So what happens is you can put it like that, but you can say, okay, what happened if I rotate it before putting it? So you can rotate 90 degrees, 180 degrees, or every time that you put it, once you rotate it one way and the other you rotate it the other way, 90 plus 90 minus 90 plus 180 minus 180. And so what that does is it changes the deformation, the direction of the deformation or of the shear with respect to the previous structure that you were deforming. So it's not accumulated shear. It could be shear and reverse shear, or it could be shear and transverse shear. Every time that you do the rotation, you shear in different directions. You have three different possibilities, and you can just keep doing that for 16 passes, let's say. Okay, so what we are going to demonstrate two of those passes today, but as you can see, one of the things that we will need to do, and this is what these matrices indicate, is that you have a certain matrix A that gives you the orientation of your crystal with respect to your sample axis, and a matrix F that is a deformation gradient that is referred also to sample axis, that gives you the shape and orientation of your grain. But when you rotate it rigidly, you need to change these tensors in order to put them back into the sample axis. So every time that you do one pass and do one of these operations, you have to first redefine these tensors and refer them again to the sample axis. Okay? So that is an operation that we are going to be doing. Now, this is what is called route BA. These are predictions that we did time ago with the VPSC code. The route BA consists in doing alternate rotation of 90 degrees clockwise and counterclockwise when you are introducing your sample again. So you turn your sample, you rotate 90 degrees, or you turn minus 90 degrees sequentially in every iteration. So what is plotted here is for 4 passes. This corresponds to doing 4 passes of the route BA. You start with a texture that is a random texture, and then at the end of the pass you have a texture that looks like this, a typical shear texture of an FCC material. But then when you rotate your texture to put it back into the sample axis, your texture looks like this now. This is very much similar to a rolling texture, okay? And the truth is, if you think about the rolling as a tensor that is 1, 0, minus 1, the velocity gradient, if you rotate that tensor by 45 degrees, if you think of a shear, epsilon 1, 2, and epsilon 2, 1, and you rotate it 45 degrees, it gives you something that is like a rolling, like a plane strain tensor. So that is what happened. We did shear at 45 degrees. So anyway, we put it through, we do another pass, we get this texture, we rotate it again, we do another pass, we get this texture, put it again, do another pass, and get this texture. So this is more or less, as you can see, the texture is kind of converging towards this type of texture. The other interesting thing is that here we did shear, and that this shear is 400% because there is a 100% in each pass. The accumulated shear is 400%. If you do 400% shear, just simple shear, 400% simple shear, the flow stress looks like this. Is the green line, okay? But in this case, the flow stress, yes, in the first pass it looks like this because it's that shear, but then after rotation, because of the different, it's a different texture and a different grain shape, grain orientation, the yield stress is up here. And then during the pass, that shear comes down here. And then you rotate it again, you start with the flow stress there, and during the pass goes there, and so on, so forth. The stress go up because you are doing shear you're doing shear here on this texture. Essentially, this is the texture that you are generating when you're doing shear. When you put it back into the die, now you're doing the same type of shear but on this texture, and so this texture wants to go to something like this, but the grains are not properly oriented because those grains you reoriented them in the first pass. You're reorienting them to make it easier to accommodate the shear, but then you just turn them around, and so the grains are not properly oriented. The Taylor factor is going to be higher, and as I said, there is no hardening here. There is only texture hardening, but there is no dislocation hardening. Only tau 0 equal 1 is the parameter used to make things clear. So that's the reason. The fact that every time that it softens, you turn it around and shear it again. So the problem in real life, this problem is not as simple as say, okay, when I go through this portion of the die, there is a sudden shear happening in this plane. In reality, the material behaves in a more complicated way. For one thing, this region here which is called the dead zone area, tends not to shear, tends to kind of accumulate, but so it's a rather odd portion of the die, and so here you don't have that shear, and in reality the shear starts before reaching this point and continues after passing this point. So if you do a finite element simulation of this problem, what you see is that I can't remember what is being plotted here really. To tell you the truth, it could be the strain. Yes, the effective strain. So you can see that the effective strain or strain rate. Yeah, there is a D there. Yes, it's the effective strain rate. The strain rate, the shear rate starts here, increases as you go through the plane, and then it decreases. Now we have, before doing this, we just propose a way of doing this gradual rotation of the shear plane using an analytic model, which gave very good results, and we published that many years ago with Irene Beyer-Line. And I'm not going to go into that, but you have, imagine that you have a plane that is rotating where shear is taking place, and as you approach the center, the shear rate is maximum, and as you move away, the shear rate goes to 0. So you apply your shear gradually into your material. But we are not going to, I mean, you can easily implement that using what we saw yesterday. If you have a variable, if you have a non-homogeneous deformation history, that analytical expression was programmed and put into VPSC as a history of deformation, and then that is what was imposed to the code. But today we are doing just simple shear. So this is one of the problems that we are going to solve today. This is called the route C. The route C involves doing repeated rotations of 180 degrees clockwise around the die axis. The die axis is this one. This route reverses the sense of shear at each pass. I explain. You put your sample, your grains are, let's say, equiax, spherical. You put it through here, you come out here, and your grains now are elongated. You have deformed by 100% shear your grains. They have that shape. But now you rotate your sample, because you have to put it back there. You rotate your sample 90 degrees, and then you rotate your sample before introducing it 180 degrees. Now this drawing is wrong. I see that now, but this drawing is wrong, because if you rotate this 180 degrees, the grain should be pointing in the other direction. The conditions are the velocity gradient in this system, 1 prime, 2 prime, where you impose the shear, are just a shear minus gamma dot. That is the boundary condition in the system. But because we work in the system of the die, we have to rotate it and put it in the system of the die, the system 1, 2. And in that system, it looks something like that. Okay, the 180 degrees clockwise rotation around the axis 3 is this matrix. So you multiply the velocity gradient, the deformation gradient, and the grain orientation by this matrix in order to give it the new orientation with respect to the old sample axis. That is going to be done as an operation when you run the code. So when you run the code, you are going to be doing four processes. In the first process, you make an equal channel angular extrusion of 50%, then you are going to make a rigid rotation of 90 degrees, and the matrices are there. Then you are going to make a rigid rotation of 180 degrees, rotate the texture in both cases by 90 like that. Once you are there, 180 like that, and then you do another extrusion process. So those four processes are there, and these files are essentially these matrices. These files point at this matrix, and this is this velocity gradient. What you will be getting now that you run that exercise is that the code will give you the texture after each pass, after each process. It will give you the texture, the final texture. So you will be getting. You start with this texture. You do 50% shear. You get this texture. Now you rotate this shear around the axis 3, which is the center, by 90 degrees. As you see, if I rotate this texture by 90 degrees, I get this texture. It's just rotated 90 degrees. And then this texture is rotated by 90 degrees. Well, this is the route VA. The route C, let's go to the bottom, because I was talking about the route C before. You have your initial texture. This is the deformation texture. You rotate 90 degrees this texture, and you get that this is just rotated in this direction of this one. And then you rotate this texture by 180 degrees around this axis, which is the axis 2, and you get that. As you can see, this one is the rotated by 180 degrees of this texture, and then you do another pass. And because this pass C reverses the sense of shear with respect to the sample that you had before, you practically recover again the random texture with which you started. So the grains go like this, or they go like this, but then with all the rotations that you did, they end up, you push them in the opposite. It's like doing shear reverse shear. And so you go back to something that is close to random. That is not the case with the route BA, because the rotation is only 90 degrees, so it's not a reversal of shear, it's a cross shear. So what I'm going to be asking you to run one of these cases, run the case C, because we have run the case C. So go to example 11, DKE, route C, copy VPSC8 into the root directory, and then run the simulation, and then the simulation will have 500 orientations, sleeping 111, 110, no strain hardening. You're doing 50 steps of shear at 45 degrees, which represents a shear of 100% in each pass. And yes, the XC entry and flow axis of the die are 1, 2, 3 respectively. And these are the clockwise and anti-clockwise. These are the rotation matrices that you need to use in those cases. They are already included in VPSC8 in, so VPSC in will go and look for this rotation matrix. So run that case, see if you can plot the texture. I'm going to do it on my own here, but mainly for the benefit of the record. So if someone looks into this record, they can see the steps. I go into example 11, and then I'm going into route C in example 11. I copy VPSC8 in, and I move it to the root directory. And once it is in the root directory, I open the DOS window and run the code. Okay. So this process took 24 seconds, which is much shorter than what it would take to you in the lab to do the same experiment. Something here. I'm going to plot the texture. Now I'm going to start new plot. Okay. So there you go. I will ask for your attention just for one moment. I plotted it this way because this shows another feature of the code Pol 8. What I asked to plot the text phase 1 dot out. Now, text phase 1 dot out contains really four texture files. So Pol 8 recognizes those and can plot all of them when they are concatenated. So what is the first equal channel angular extrusion? The other is the texture rotated 90 degrees. The other is the texture rotated 180 degrees. And the other is the equal channel angular extrusion. So there are four groups of files there. In addition to this, I asked to plot three poles. And the three poles are the 100, the 110, and the 111. Now, we haven't had time really to make these plots nice, so the labels disappear there, so you really have to know what you are plotting. But what we are plotting here then is this is the 100 for the first equal channel angular extrusion, 90-degree rotation, 180-degree rotation, equal channel angular extrusion. And the same for the 110 and the same for the 111. Okay. Now it is interesting because you see that yes, this texture is closer to random, but it's not really random. There is some components are kind of preserved, and that partly has to do with the fact that the grain shape. The other interesting thing, we are going to take a look at that. What happened with the average grain shape in this case? Because the grain shape is supposed to be distorted, but then it's supposed to go back to being undistorted. But of course, that process is not completely reversible because the environment that the grain sees is different for every grain. Let me take a look at that, and I'll bring the texture file on the screen. So you see here after the first pass, the length of the axis of the average ellipsoid is 1.2, and 0.4. 1.2, and 0.4. And those are the eigenvalues of the deformation gradient, those values. As you can see, what is happening is the length of the average ellipsoid axis for the second pass is 1, 1, and 0.5. So it hasn't really go back to be a sphere, but it has reduced the ellipticity, the ellipsoid. Have you guys been able to run the problem and plot something? The stress strain curve is probably an interesting one because you should see that high flow goes down, and then when you reload it, the flow is again high, and then it goes out. By the way, just so it has 104 lines. So these are two passes of 50 steps each. Okay. So the first pass is the first equal channel angular extrusion, and then you do the rigid rotation, but there is no stress associated with those because you just rotate rigidly your sample, and then you do the next pass, and those are the stresses. Yes, and yes, if you look at the stress, I guess that we are looking at the stress 1, 2, 0.28, 0.29, 0.26, 0.22. Yeah, it has a minimum of 0.22. It goes from 0.29. Now, I remind you, this is the deviatoric. This is the deviatoric stress. Um, Probably the von Mises is the one you should be looking at, which is the second column, because in this problem we cannot calculate the Cauchy stress because the boundary conditions don't allow us to calculate the Cauchy stress. If the boundary conditions say that you know one of the boundary stress components, then you can calculate the Cauchy stress, the macroscopic, not the one in the grain, the macroscopic. And then we list the Cauchy stress here, the six components. But if you look at the deviatoric, you should be looking at the deviatoric in this problem. And yes, it goes from 2.5 here to 2 point. It doesn't change much really. Yeah, 2.4. It's not changing much. The result that I showed before, that plot is an old one. I really should be looking into if there is some inconsistency or what we plot at that time. But yeah, that's what you are getting. Oh, because the one I showed you before was for the route BC or BA, the route BA. It was not this one. And in the route BA, you are not reversing sense. You are shearing across, and it will give you higher values. That's why. That's why, yes, the result I showed before, which was this one. You see that here is more like now I don't know what is being plotted here really. I have to go back to the paper and take a look. But you see that it starts at 1.2 and then 1.3 here and 1.4 here. So I need to look at what was plotted here, but I expect a larger variation for the route VA. This is hardening. The hardening is 1. There is no hardening. Tau 0 is 1, so it could be one whatever it is. So it can be 1 ton, 1 GPa, 1 MPa. Is 1 in some unit. as far as the units are consistent, is 1. It stays like that.